Hello, my name is Alexander Rodriguez, and I'm going to be presenting our work titled Incorporating Expert Guidance in Epidemic Forecasting. My co-authors are Bijaya Adhikari from University of Iowa, Naren Ramakrishnan from Virginia Tech, and Aditya Prakash from Georgia Tech. Our motivating set is influenza, which is a contagious respiratory illness. Some of its symptoms include fever, cough, sore throat, and runny nose. Influenza incurs in a heavy burden for the world. Only in the US, in the season 2018 to 2019, we had around 20k deaths, 300k hospitalizations, and an annual economic impact higher than $26 billion. Can data science tool be used to help this problem? One successful application of our tools has been in forecasting. Why forecasting influenza? Because it helps resource and budget allocation for public health entities, ensure preparedness, and supports decision making and public policy. Let me introduce you to the influenza forecasting problem in an informal way. You can see here that we have the incidence curve observed until the current week, and the current week is marked with a green dashed line in the plot in the right. And we want to predict some characteristics of this curve for the future. The data that we use is surveillance data from CDC, which is collected from a network of healthcare providers which report the percentage of visitors related to influenza-like illnesses. We can state our problem more formally as follows. Given some historical seasons, as depicted in the right plot, partially observed influenza incidence curve until week T for the current season, we want to predict what are going to be the future incidences. For example, the next 4 incidences of this curve. We want to predict the peak intensity, the peak time, and the onset, which is when the influenza season is going to take off. A data-driven approach was proposed by Adhikari at SIGKDD 2019. This is a deep learning approach for forecasting influenza based on historical data. It forecasts multiple targets as the ones in the previous slide, and is one of the first deep learning based approaches for influenza forecasting. It performs well in real-time forecasting. It was placed first in the HHS Region 1 in 2018 to 2019 Flu Safe Challenge, which is hosted by CDC. Let me now introduce the problem that we address in this paper, which is incorporating guidance in epidemic forecasting. Epidemiological experts may notice an ideal behavior exhibited by statistical approaches. For example, we have what is known in literature as Christmas dip. Epidemiological experts know that during the holiday season of Christmas, people change their care-seeking behavior, and there is this smooth dip. However, data-driven models often overcorrect this dip. Perhaps incorporating guidance from epidemiological experts about the smoothness of this dip may help to overcome this issue. Therefore, our question is how to enforce epidemic forecasting models to incorporate expert guidance to show desirable properties. Our approach leverages a Seldonian optimization framework, which was introduced by Thomas in 2019. It was proposed for AI safety, and it aims to preclude undesirable behavior of an AI model by enforcing behavioral constraints in optimization. Has a safety test in observed data in order to achieve this goal. Our idea is to adapt the Seldonian framework on EPIDEEP optimization to incorporate expert guidance. Our approach is called expert-guided epiDEEP. We present the epiDEEP's loss function, which we can extract as a forecasting loss plus some internal representation loss. For guided epiDEEP, we include a probabilistic constraint in which first we have to define the guidance function, and this guidance function is bounded by epsilon. And meeting this bound is a desirable behavior that we want to enforce. Therefore, we want to make the probability of guidance being satisfied to be at least 1 minus some small number delta. How do we define the guidance function? The guidance function that we use is smoothness, which we define as the maximum allowed difference epsilon between the predicted value and its predecessor. So this is the function, is the expected value of the absolute value, the absolute difference between the forecasted value and the predecessor. The guidance is then satisfied when this expected value is below the epsilon, with a probability of at least 1 minus delta. Our training process is based on the Selonian approach. Guided epiDEEP, our algorithm, first partitions the training data D into disjoint sets DC and DS. DC is the candidate selection set, and DS is the safety test set. Then it uses the candidate selection set to obtain one candidate solution. This candidate solution is going to be evaluated in the safety test, which is performing in the safety test set DS. Basically, here we are ensuring that the guidance is being met. If the solution does meet the guidance, then we are going to return the candidate solution as the solution of the algorithm. Otherwise, we're going to return no solution found, NSF. For our experiments, we use the following dataset. We use a public available WI surveillance data released by CDC. The available years are since 1997 to 2019, and is available at this URL. These experiments are in the Christmas tip, where we want to enforce our predictions to be smooth so that we avoid them to overcorrect. For the plots, the x-axis represents several competitive methods, including us. For the left plot, the y-axis is the undesirable behavior related to the smoothness that we want to minimize. The goal of the guidance is to make sure that we are below the red dashed line, which represents the threshold epsilon. Our method performance is represented as a green bar, and next to it is normal epiDEEP. We can clearly see the improvement in meeting the guidance, which in this case is also reflected in RMSE performance in the plot in the right. Therefore, guided epiDEEP meets the guidance constraint while also minimizing performance error. Conclusions. We presented a flexible and adaptable framework to incorporate expert guidance. Our results show that the guidance can be met with a probabilistic tolerance, but also maintaining performance accuracy. Thank you for your attention. If you have any questions, please contact us at this email.